So just to remind you, dual vector space is defined as a set of linear functions, the space of linear functions on a given vector space, right? We define this. So suppose a vector space S is given, you define S tilde, which is the set of all linear functions on S. Yeah? And then you define the rule of addition of the linear functions, multiplication by numbers, etc. And we showed that that was a vector space, right? And furthermore, we showed that it was exactly n-dimensional. So the same dimension as the dimension of S, which is a bit strange because you would imagine the space of functions is infinite dimensional, but the point is it's not arbitrary functions. Those are linear functions. Linear function is a very, very strong restriction, right? That's why it becomes finally only n-dimensional, right? And finally, in the case where a scalar product is defined in the original vector space S, then there is a natural map, a one-to-one map between S and S tilde. So you can associate to a vector S a vector in S tilde. Okay? So we said, I mean, so we have S tilde, which was the set of linear functions on S, where S is an n-dimensional vector space. Then the first thing we showed was S tilde is also n-dimensional. Right? And you remember how we showed it, we just constructed a basis for S tilde, right? So if, let's say, I are the basis, I going from 1 to n is a basis for S, then we defined a basis for S tilde. We defined linear functions which we called Fi. These are linear functions, and they are defined by the following conditions. Fi acting on J is delta Ij. Right? This is just I just chose. It doesn't have to be like that. You could choose any basis, as you know. Given a vector space, if I choose one basis, you may choose another basis, right? So, but this is just a convenient basis. Right? Then this I again goes from 1 to n. And we showed that this, in fact, is a basis for, meaning any vector, any linear function can be expanded as linear combinations of these Fi's, right? That is, so, and we showed also that these Fi's were linearly independent of each other, right? So therefore, that is how we proved that this has the same dimension. Okay. Finally, if a scalar product is given, you see, I want to emphasize, to define the dual vector space, you don't need scalar product in the original vector space S. Even without a scalar product definition in the original vector space, you can always define S tilde. There's no problem, right? However, if a scalar product is given to you, if a scalar product exists or is defined on S, if a scalar product is defined on S, then for every vector A, I can associate a particular vector, a vector in S tilde. We can give a map, one-to-one map. For A, I define a vector in S tilde, which we will denote always like this. So this is a notation. I'm just denoting. I'm saying there is a map, a unique vector. I mean, given a vector A, there is a unique vector in S tilde. I can give a map like that. Okay? And I will denote that vector by A. This is a notation. So specifically, what will be A? A will be, I can write this A as, I think, AI Fi, summed over I. Okay. So this is a map. So you see, for a given A, I associate a particular vector in S tilde, which is this. I define this vector, and I just call this as that. Okay. Where what is this? This is the scalar product, which is given, which has been defined. Okay. That's a scalar product between A, the vector A, and the basis vector I. Okay. It will be some number, some complex number. I mean, that goes into the definition, the way you have defined the scalar product. Okay. But once you have defined, then this will be some complex numbers, right? And I'm just adding, taking linear combination of Fi's with these multiplying these complex numbers. So there will be some vector in S tilde, some linear function, right? And what I'm saying is that this, so I will give an association. This vector will be associated with that dual vector, and this one I just give a notation. I call that as A. Okay. Note that this map is anti-linear map. Anti-linear map. Why? Because suppose I had taken, say A is mapped to that, right? Now let's ask the question: what happens to alpha A? Where is that mapped to? Right? Alpha is again a vector of S. You can ask where does it map to? Well, we again apply the same formula. So this will be mapped to sum I equal to 1 to n. You see AI, but remember what is AI is the same as IA complex conjugate, right? The scalar product satisfies that condition. But now you see instead of A I have alpha A, right? So it will be, so in other words it's I alpha A, right? Alpha is a number. But remember this is linear, so you get here I equal to 1 to n alpha IA whole thing complex conjugate, because the complex conjugate is over everything, right, times Fi, which is the same as, okay, you take the complex conjugate, so you get I equal to 1 to n alpha bar, okay, and then complex conjugate of IA is by definition again AI Fi. So you see alpha bar comes out, and what is remaining is simply the A, right? So this is the same as, I mean the dual vector A. So this is the same as alpha bar dual vector A. So you see if A is mapped to that, then alpha times A is mapped to alpha bar times A. So in that sense it's an anti-linear map, this map, but it's a one-to-one map. It's a one-to-one map. It's a natural map once you give a scalar product. This is the reason why in quantum mechanics you will see that whenever you go to so you have a ket state. When you go to the bra state, you have to take the complex conjugation, right? That is the reason. Okay. I mean, you will see that in more detail in quantum mechanics course, no? But okay. All right. So now, is there any question on this? Please feel free to ask questions and don't be shy. Okay. And so now, what I will do is. Yeah, there are two things. So then towards the end of last lecture, we also showed that given the definition of scalar product, the scalar product satisfies the Cauchy-Schwarz inequality, right? That was an important point. So let me go back now. This was just to remind, because I'm afraid that this is a little abstract. This definition is a little abstract, but you will get used to it. Okay, so the scalar product, the main property was for any two vectors A and B, we had this was a complex number. This is just a notation. It's a scalar product between A and B. It's a complex number which satisfies the condition that AB is the same as complex conjugate of BA. There was one thing. And the second important point was that AA, this is linear. I mean, second is a linear in this argument. So in other words, if C is equal to alpha B plus beta D, let's say. Huh? Yeah. I mean, it's just I just chose some combination, right? Then A with C is the same as alpha A with B plus beta A with D. So that's a linear condition. But of course, by using the fact that when you exchange the order, it becomes complex conjugate. From here, it also implies that it will be anti-linear in the second argument. Linear in the first argument, this argument, but anti-linear in this one. Just taking the complex conjugate, you'll see. Okay. And the third one, very important property, was AA. Well, by this, it immediately follows that it is also the complex conjugate of that. Right? So that means it's real. But so for sure this is real, but what we are saying is that actually it is is a positive, I mean non-negative, is greater than or equal to 0. And it is 0, and this is 0 if and only if A is a null vector. Only in that case it is 0, otherwise it's strictly positive. And it's from these things we proved the Cauchy-Schwarz inequality. Which was a statement that if I give you two vectors, so A, B, scalar product, modulus of that is less than or equal to the square root of AA and BB. This is the analog of what we saw in what we already are familiar with in the usual vectors. No? If you take two vectors, the dot product of that will be the length of one vector times the length of the other vector times the cosine of the angle between the two, right? So since cosine is modulus of cosine is always less than or equal to 1, therefore from that you know that the dot product is going to be always, I mean modulus of dot product is always going to be less than the length product of the length of the two vectors, less than or equal to. It will be equal to only if they are parallel or anti-parallel, right? Only in that case. Otherwise, it will be always. So this is just that. You see, so what we are saying is that with these definitions, it follows this property.
Question. Yeah. Maybe from how we derived the Cauchy-Schwarz inequality, where was the C coming from? How did you pick the C?
This is the thing. Yeah, good. I mean. Yeah, so, right, I mean, that is a trick, right? I mean, yeah, true, it is not immediately obvious that this is how you should start, right?
Yeah.
It's not immediately obvious. Yeah, it's not obvious, but I mean, many times that happens. You see, in giving a proof of some theorem, the starting point is not immediately obvious. I mean, that is where the great mathematicians, do some work. No? You need some special way of thinking about things to, right, to be able to prove.
We just take it as it is.
Yeah, I mean the starting point. Yeah, that's the way it is. I don't know if there's some other way of proving it. I mean, maybe there exists some other ways of proving it. One has to think about it. If there is some other way, other route to prove the same thing. But yeah, many times proving the theorem, it's almost obvious. This is how you should start. But in this case, yeah, it is not obvious why the whoever proved this the first time, why he even thought about this, no? Yeah, it's not obvious, right? Okay, so this was one. Then you're also familiar with another property from our usual experience with the vectors, right? If I take in a plane two vectors, let's say this vector and so that vector, let's say, okay. Then we know that if I take so this is say A and that's B, then the sum of the two vectors is this. You have to draw the parallelogram, okay, and this is the vector, right? This is A plus B. Okay. So of course this is A, and I mean these two are parallel, so this is also B, right? This vector. So the triangular inequality says that the length of this is going to be less than or equal to the sum of these two lengths, right? That is a triangular inequality. So the length of A plus B is less than or equal to the length of A plus length of B. Right? It will be equal, of course, if B was parallel to A. Right? In that case, they just add up. So the A plus B will be simply the length of A. But if they're not parallel, then it will be always less than or equal to A plus B. Right? That's the. Yep. So let's see how do you prove that. Huh? Now, so this is true, but now we want to show that just from these definitions that we gave, these abstract definitions that we gave for the scalar product, right? I mean, this is a particular example, right? This is a particular on the plane. Okay, we know that this is what happens, right? But now we want to show that in general, these definitions that we have given, they will also with that definition again, the scalar product will satisfy this condition. That's what we want to prove. Okay, so let's so try to prove that. So let's say suppose I'm given a vector A and a vector B. Then of course I ask the question what happens to A plus B, the length of that. Okay, the length of this. The length, remember what is the length? The length is simply given by the length of A is simply this square root of that, right? I mean, this is A with A scalar product is like A square, the length square. I mean, that would be what you would get there, and the square root of that is the length. So we define this as the length of the vector A. Yes. So I want to take the length of this. So length of this guy. Okay. So let me just call it, give it a name. So this is some vector C. C is A plus B, right? So what I want to compute, I want to compute C with C. First of all, and then take the square root. So this will be length square of the vector C. So let's first compute that. That will be the same as C with A plus B. So CA plus CB, I just use a linearity here because this C is A plus B, so I just use a linearity, right? Then again I use the linearity here, so I will get here A plus BA plus AB plus BB, right? I mean this is a sum of these two terms, and that is a sum of those two terms, right? Because C is A plus B. I mean, since this is, so therefore C is also equal to A plus B. Okay. So what is this? This is the AA plus BB plus, so you see you have AB plus BA, but BA is the complex conjugate of that, right? So this quantity is 2 times the real part of AB, right? What is the real part? I mean, in general, if I give you a complex number Z, this will be some real number plus I times some another real number, right? This is general complex number. So the real part of Z is the X, and the imaginary part of Z is Y. So since I have, so let me call this as Z, then this will be Z, this is a complex conjugate, this will be Z bar. Z bar will be X minus IY. So when you add them up, IY will cancel, and you will just get 2 times X. So it's 2 times the real part of it. Okay. So that's the first step. But so this I can write again as this is going to be less than or equal to. Okay. You see, this is a real part of AB, right? But I can write it in this way. This is going to be less than or equal to 2 times the magnitude of AB. Correct? I mean, what is the magnitude of Z? What is the magnitude of Z? Complex number. It is simply square root of X square plus Y square. Correct? So now what we are saying is the real, this is 2 times the real part of Z. So this guy is 2 times X. So the point is that this is greater than or equal to X, right? Isn't it? I mean, we have a square root of X square plus Y square. This is going to be greater than or equal to the magnitude of X. Correct? Because you have I mean, if Y was not there, then square root of X square is exactly equal to modulus of X, right? But now I'm adding some positive number because Y square is a positive quantity, right? The square of any number will be always positive. Right? So you're adding something to what was before. So this is going to be greater than or equal to that. It will be equal if Y was 0, right? Otherwise, it's going to be generally greater. So that's what I've done. I have replaced this by this quantity, the absolute value. This is just a real part of that, right? Of this complex number. Now I'm taking the absolute value of that complex number. So this is going to be greater than or equal to that, right? So therefore, this whole thing is going to be greater than or equal to that. Okay. Now I use the Cauchy-Schwarz inequality. We already know the Cauchy-Schwarz inequality for that, right? So let's see. So Cauchy-Schwarz inequality says that the absolute value of AB is less than or equal to square root of AA times BB. Right? So I just use this here. So we find that so from this we find that CC is less than or equal to AA plus BB plus 2 times. Now we have absolute value of AB, but that is going to be is less than or equal to that. So I just substitute this here. So you get here AA times BB. Right? I mean, this whole thing is going to be greater than or equal to that whole thing. Right? But this is already greater than or equal to CC. Right? So therefore, so CC is also less than or equal to this quantity. But this guy is a whole square. This guy is nothing else but square root of AA plus square root of BB whole square. Right? If you take the whole square, I mean just open the bracket. So square of that, which is this, plus square of that, which is that, and then the cross product 2 times this times that, which is that. Okay. So this is this. So we have come to this conclusion that CC is less than or equal to that. And that's what we wanted to prove. Just take the square root on both sides, right? So this implies that square root of CC, which is the length of C, is less than or equal to the length of A plus the length of B. This is the triangular inequality. Okay. I mean, this is possible because, I mean, because these are all positive quantities. That's why this is true. I mean, if this was somehow this is negative, if there were negative quantities, then you cannot write like this. But since you know that every single term here is positive, I mean non-negative, right? So you can take the square root on both sides. Okay, is that clear? I mean, all right. So that's a triangular inequality. Now we go to. Okay, there's something. Yeah. Any question here? Because then I can erase. If you don't have any question, I can erase that part. Yes, okay. Yeah. No questions? All right. I mean, the purpose of this is to show that our scalar product that we have defined is makes perfect sense. I mean, it satisfies all the intuition that you have from the plane, from the vectors on the plane. They satisfy all these conditions, right? But now you see that even in general, this definition satisfies these conditions. Okay. Now another notion is, if you take say plane, for example, you have say various points, right? I mean, take a point here, a point here. Given a point, you can always draw a vector, right? Starting from the origin, you can draw a vector like that, a vector like that. But you have a notion whether these 2 points are near or far, right? How do you say given 2 points, are they near or are they far from each other? Well, all you do is you just compute the distance of these two, distance between the two, right? If the distance is small, you say they are near. If the distance is large, you say they are far, right? So there's a notion of closeness. What's the distance between 2 vectors? Between 2 points is the same as between 2 vectors, because given a point, I know I can draw a vector, right? So how close are 2 vectors? How far they are? That depends on the distance, right? But which distance? Is this distance. So if I give you a vector A, a vector B, right? Then you look at this vector, which is say B minus A or A minus B, doesn't matter. A minus B would be opposite direction. and then you take the length of that, right? Length of this vector. And that is what you mean by distance between the 2 points. So given a scalar product, you can immediately define a notion of distance between 2 vectors. Now in general, not just in the plane, but in general, right? So idea is exactly that. So if you give me 2 vectors A and B, then the distance between that, and which we'll denote by rho, this is a distance, that's a distance between, and I will write it like this, rho AB. This is by definition, I mean we can define it like this, is the length of A minus B. Is it's equal to the length of this vector. So what are the things? First of all, notice that this is the order doesn't matter here. I mean, rho of BA is the same as rho of AB, because if you want to compute the for the rho of BA according to this formula, it would be the distance. It will be the length of the B minus A. But the length of B minus A is the length same as the length of A minus B, right? So this remains the same. This is what you would imagine. I mean, given 2 points, I mean, there's the distance is just given. I mean, it doesn't matter whether you say distance between point number 1 and point number 2, or distance between point number 2 and point number 1, the same. So this is the property. The second property is that if a distance between 2 points, A and B, is 0, suppose the distance between 2 points is 0, between two particular vectors is 0, then this implies that A equal to B. Right? Because again, by definition, this is the length of A minus B, but the length of A minus B, if it is 0, that can only happen if this vector is 0, but if this vector is 0, then A is equal to B. Right? So that's this. And then the triangular inequality. The distance again satisfies the triangular inequality. I mean, for the same reason, and that we have already shown. So the point is that the notion of distance satisfies these important properties. That the distance is, I mean, it doesn't matter. The distance between point number 1 and point number 2 is the same as the one between point 2 and point 1. It's always non-negative. These are always non-negative because the length is always non-negative, right? So this is always non-negative. Okay. And it is 0 only if A is equal to B. Right? When A is not equal to B, it is not 0, it's a positive. Okay. And finally, they should satisfy the triangular inequality. Right? These are the basic properties of the distance. It's okay, we will not be using this notion of distance so much here, but it's important in topology. I mean, you know, given a space, you always need to know, you need to define what do you mean by nearby points, a neighborhood of that point, right? Because if you want to set up all the calculus and all that, you need to know the notion of a near points. No? Which point is nearby? So that's crucial. To develop all the calculus, differentiation, all this notion, you need that. But we will not be doing it. So I will not be saying more about the distance function. Okay? Just for you to know that there is this notion. Okay. Now we come to a very important point, which is very useful, I think. Which will be very useful for all the quantum mechanics and basically everything which uses vector spaces. And that is the notion of an orthogonal basis. Orthogonal basis. You see, so far we talked about a basis. So what was the basis? Basis was a set of a maximal set of linearly independent vectors, right? And you see that for that notion, I never introduced any metric. There was no notion of a scalar product, right? It was a purely vector space structure. But now we have more structure on that, right? Now we have defined also a scalar product in this. So we can do a bit better than before, right? In other words, we can choose perhaps some particularly nice basis, right? So what we'll do is we'll talk about something called orthogonal basis. Okay. So first of all, let me define what is an orthogonal vector. What are the orthogonal vectors? If if I give you some two vectors A and B which satisfy the condition A with B is 0, okay, then A and B are called orthogonal to each other. So that's the definition of orthogonal. Orthogonal to each other. So in the example of the flat in the plane, in the example of plane, if I give you one vector here, and if I go to a perpendicular direction, so this is say the vector A, and any vector perpendicular to B will be orthogonal, right? Because the dot product will be A, length of A times length of B times cosine of that angle, but this is 90 degrees, so cosine of 90 is 0, so this dot product will be 0, right? So in this case, A and B will be orthogonal to each other, right? So that is the idea here. So we do this. So what is now an orthogonal basis? Orthogonal basis is that the basis vectors are all orthogonal to each other. Okay. So if you have n-dimensional space, there will be n basis vectors, right? But we choose a particular set of basis vectors. You remember, in the choice of basis, there is a lot of, lot of freedom there, right? You can choose different bases, right? But an orthogonal basis is that basis vector, the set of those basis vectors which are orthogonal to each other. Okay, that's so in particular, for example, in the two-dimensional case, you see, what do we choose? We don't choose just generally. Normally we choose this basis vectors, right? Let me call it 1. I don't know, A. Say, I don't know, 1. A. Okay. And another basis vector which is in the y-axis. This is the x-axis, this is the y-axis, right? These are orthogonal to each other. This is what we normally choose. No, we don't choose we don't choose, say, one of them is that, this one, another B. Although you could choose this as a basis vector, there's no problem with that, right? As we saw, these are linearly independent, right? However, it's more convenient for many applications. It's more convenient to use an orthogonal basis, where you choose, say, one of them along the x-axis, other along the y-axis. Okay, it's much easier. Why is it easier? Because if I take any vector v, if I write it as a linear combination of these two vectors, okay, let me use another symbol here, E1 and E2. Okay, two orthogonal vectors. So if I write v as a linear combination of E1 plus E2 with some coefficients, what are these coefficients? These coefficients will be just take the projected. So this will be some x, this length, and if you project here, this will be some length y. Then this will be simply x E1 plus y E2, right? And then v square, the length v dot v, is simply x square plus y square, right? Because why? Because E1 square is 1, E2 square is 1, and E1 dot E2 is 0. This is the reason. This is the reason why you have x square plus y square, right? So it's much more convenient. Yeah. In fact, in quantum mechanics, you'll be many times using the orthogonal basis. So that's why it's useful to. Because of this reason, everything becomes simpler. All the formulae become much simpler if you use orthogonal basis. So I will always use the symbol for orthogonal basis in general. So this will be some E1, E2, En. If it's an n-dimensional space, there will be, of course, n basis vectors should be n vectors. But now I'm choosing a particular basis vectors such that they are orthogonal to each other. Okay. So what they satisfy then? Let me write down. Okay. So orthogonal basis satisfies this condition. EI with EJ is equal to delta IJ. Delta IJ. Kronecker delta. So remember, this is a Kronecker delta. This will appear all the time. So you should be familiar with this Kronecker delta. I think you already seen it before, right? The Kronecker delta. So this is equal to 1 if I is equal to j. It is 0 if I is not equal to j. That's the definition of conical delta. Okay. Any question? You had a question? No. You didn't have any question. Okay. No, I thought you were asking a question. No, all right. Okay. Okay. Fine. So we want to choose it. So first question you can ask, is it possible to choose it? I mean, for a given any vector space, is it always possible to choose such a basis? That's the first question you can ask. Answer to that is yes. So there's a theorem. There's a theorem, orthogonalization theorem. Orthogonalization theorem, or it's also called the Graham-Schmidt procedure. Graham-Schmidt method. Okay. So there's a theorem which says that it's always possible to choose an orthogonal basis. The reason why, I mean, the proof of the theorem is actually constructive proof, in the sense that the proof is given by explicitly constructing it, okay? Or at least it gives a procedure how to construct it, a method how to construct it, recursively, step by step by step. And that's why it's also called Graham-Schmidt method, because this gives you a method how to construct orthogonal basis. Okay. So let me just describe that. So the procedure is actually completely straightforward. Well, suppose I am given some basis, which I call I. This is some basis. Is a basis, which need not be orthogonal. Just some basis. I goes from 1 to n. Okay. Now, given this basis, which is an arbitrary basis, I want to construct an orthogonal basis. This is the aim, right? This is what we want to do. So how will we do that? Okay, let me take the first vector. Okay. Well, this vector, okay, is one vector, but its length may not be equal to 1, right? Because here you see E1 with E1 is 1, right? So its length may not be equal to 1. But that's not a big problem. I can always divide by the length, right? I take this vector and divide by the length. Then it will become something of length 1, right? So let's define E1 as this divided by square root of the length. I mean the length, square root of 1 with square root of 1 with 1. Okay, this is the length of the first vector. Right? So if you define this vector, then clearly E1 with E1 is 1, right? I mean, this is a number. Sorry, let me write it like this. Better to write it like that. 1 over square root of 1, 1, 1. Okay, this is a number. So I'm just multiplying that number to this vector, which is again a vector, right? Okay. Now this is immediate to check. You can check immediately that E1 with E1 is in fact 1. Why? Because you see this is a positive number. It's a positive number. So when I take the dual, I have to take the complex conjugate of that. But since it's a positive number, it's the same. It's a real number. It's the same, right? So you just get the square of this guy, which is 1 with 1, 1. And then the scalar product of 1 with 1. Right? It becomes, because, is it clear? I mean, again, I've done two steps in one. I mean, this factor will appear both in the vector E1 and the dual vector. Right? So you get the square of this factor, which is why you get that. And then the scalar product of this with its dual vector, which is this. And this indeed cancels and gives you 1. So E1 is of length 1. Okay, fine. Now let's go to I want to take the vector 2. I want to construct a second vector which is orthogonal to that. So what I will do, well, I can take the vector 2, okay, but the vector 2 may not be orthogonal to vector 1, right? Because as we said, this is an arbitrary basis. This need not be orthogonal. So what should I do? I mean, so again, the intuition, to get an intuition, let me again go to the plane, okay? Let me choose the first vector as that, okay, and the second vector as that. This is linearly independent, but it's not orthogonal, right? So what did I do? In the first step, what I did was I first normalized this to length 1, right? At the moment, this may not be length 1, right? So when I divide by its length, so that this becomes length 1, this I call E1. Okay, this is length 1 in some scale. Okay, this is length 1. Now, if I take the second vector, the E2 cannot be just the second vector, because second vector is not orthogonal to that, right? So what should I do? I can just take it, project it onto this axis, right, and subtract from this vector that vector. You see? So okay, let me. It's a bit cut. So say the second vector is that. What I do, I apply the projection. I draw a perpendicular here. Okay. Then whatever this is, this vector, you subtract from this vector that vector. When you subtract, so let me call this vector as 3, vector number 3, from here to here. So take 2 minus 3. Sorry, I'm sometimes using, okay, let me just use a cat notation. 2 minus 3. 2 minus 3 will be this vector minus that vector, which will be that vector. Right? Now 2 minus 3 is clearly orthogonal to the x-axis. Right? So you first construct 2 minus 3, but this may not be of length 1. So once again, just divide by the length of this vector. Right? So that way you can construct the second orthogonal vector. Right? Is that clear or not? Huh? Clear, yeah? For everyone? It's clear? Yeah. So once again, maybe I should draw the picture a bit bigger. So first vector, I choose this. Okay. The second vector, I choose something like that. This forms a basis. So this is my first vector, and this is my second vector. Okay. This is a basis, but it's not an orthogonal basis, because the dot product of these two is not 0. Right? So first of all, as a first step, I just picked one of these two vectors and just divided by the length of that vector to make it length 1. Okay, that was the easy part. Okay, so I just divide by the length of this, square root of that, and whatever I get, it will be I call E1. Okay, you see, it's going to be the same direction as 1. I'm just dividing by the length, so it's just the same direction. But now its length is 1. Right? This vector's length is 1. Now I take the second vector. Second vector is not orthogonal. But what I can do is I can I draw a perpendicular here. Okay, this will intersect at some point. This will be and draw this vector, joining this point to that point, origin to that. Okay, call this vector vector 3. Okay. Now take the difference between the vector 2 and vector 3. That difference will be simply this. This will be the vector 2 minus vector 3. Right? Because one way to see that this vector plus that vector is equal to that vector. Right? So therefore, this will be equal to this minus that. Okay. So this vector is going to be orthogonal to E1 because this is along the y-axis. Right? So this will be orthogonal to that, but now of course its length may not be equal to 1. So to get the second orthonormal vector, I just divide by the length of this. That way I construct the second orthonormal vector. Right? And you keep proceeding. Then once you have the first and second vector, take the third vector and find again, remove the projections along the first and second vector, right? And get something which is perpendicular to the first and second. So this, you keep going on and on. Okay? This is a recursive kind of procedure. So let's just formalize, write it down. So what is the second vector then? I will first take the vector 2 and subtract from that this guy. So E1, vector 2, E1. Subtract from that. This is the analog of the dot, yeah, projection, exactly. Projection onto the first direction. You take the second vector, take the projection along this first vector, and then you see that is the kind of the length of the projection, right? But then you're drawing this vector along the E1 direction. So that's why I have E1 vector. And now I subtract. Okay. So this is what I call vector 3. This is vector 3. Okay. So let's check first of all. We want to check whether this is orthogonal to E1 or not. Right? Its length is not equal to 1 yet, but that is the easy part. I can always divide by the length. But first of all, let's check whether this is orthogonal to E1. Right? So let's call this some vector I don't know, 2 prime or something. Some vector 2 prime. Call it. So I want to check whether this is orthogonal to 2 prime E1 or not. So let's do that. So what is this? Well, so 2 prime is that. So this is the same as E1 with 2 minus, this is just a number. I'm just using linearity. E1, 2, and then E1 with E1. Right? But this guy is 1 that I have already arranged. E1 with E1 is 1. Right? So this is 1. So this cancels. So you get 0. Okay? So we have shown that this vector 2 prime is indeed orthogonal to E1. The only thing which we don't know, which we still have not arranged, is to make this length equal to 1. But that is simple. So you just define E2 as 2 prime, the vector 2 prime, divided by the length of 2 prime. Okay. The length of 2 prime is simply 2 prime square. This is the length, right? That will be now, that gives you the second orthogonal vector. Now you can keep going. Now for the third vector, what I have to do, take the third vector, and then I have to remove from it the projection along the first and second. Okay. So now I can write down a general formula. I can write down. So suppose I have done this procedure up to some, I have constructed the first k orthogonal vectors. Now I want to construct the k plus 1th. This is by induction. This procedure is called induction. By induction, you want to prove this. So suppose I have gone through this procedure and constructed the first k orthogonal vectors. Now I want to show that then I can construct the k plus 1th orthogonal vector. Right? So suppose by this procedure, we have constructed the first k orthogonal vectors. Okay. Then we want to construct the k plus 1th vector. K plus 1 orthogonal vector. Okay. So I'll just write down the formula and then you will see that that is indeed the case. So I will write down first of all, let me define the k plus 1 prime vector. Okay? Because this length may not be equal to 1. Then I will divide by the length to construct. This will I define like this, k plus 1 minus EI k plus 1 EI, where I goes from 1 up to k. You see, we said that suppose we have constructed the first k orthogonal vectors, right? This EI, I goes from 1 to k. These are the orthogonal vectors. Okay? Then this is just a projection of the k plus 1th vector along this EI. Right? This is the projection. And then I sum them up and subtract from the original vector. Then this guy is going to be orthogonal to all of these EIs from 1 to k. So let's check that. So we want to check EJ with k plus 1 prime, I mean this vector, where for j, where j is between 1 and k. Because I have defined this only for 1 up to k. So far I have only constructed, under this assumption, I have only constructed the first k objects. So I want to check this expression, this thing, which, well, again use the linearity. So you get here Ej k plus 1 minus, this is just the numbers. These are the numbers. And then I take the Ej with Ei. Right? But this, we are saying both j and I are between 1 and k. So these guys are already orthogonal. So therefore, this is nothing else but the Kronecker delta. Right? Now I sum over I from 1 to k. Only time it will be non-zero is when I is equal to j. And when I is equal to j, this is simply Ej with k plus 1, which cancels with that. Okay? So this gives you 0. So indeed, this vector k plus 1 prime vector that we have constructed is orthogonal to all the first k orthogonal vectors. Okay? Only thing that is its length may not be equal to 1. Right? So I can divide by the length of this. Right? So then I define the Ek plus 1. Ek plus 1 is equal to the vector k plus 1 prime divided by the length of this vector. Okay, the length of that. And then that becomes of length 1. Right? So this procedure goes on. You can completely, and all the way up to the full n. If it's n dimensional, you can construct this way all the n orthogonal vectors. Right? This is the procedure. Note that in this procedure, the ek plus 1th vector involves only the k plus 1th vector of the original basis and lower ones, because you see, in the way we are constructing, how we construct, I think that's one important point to remember with this Graham-Schmidt procedure. Right? See, what did we do? E1 was just proportional to 1, was 1 times some number, right, divided by the length is a number. So it's basically, let me just write that, proportional to 1, right? It's just this is simply this divided by the length of that. So, okay, E2 is a linear combination. Remember how we obtained that? This was simply 2 minus E1, 2 with 1 divided by again the length of this vector. I mean, so length of that vector. Okay? But notice, so what is it? The only two vectors which are entering here is 2 and 1. Is a linear combination of second and first vector. Right? Now I go to the 3 in this procedure. This we start with again 3 minus E1 with 3 times E1. Sorry, this is E1 now. E1 is again proportional to 1, so this is again 1. Right? E1 plus E2 dot 3, E2 with 3, E2. Okay, this divided again by the length of this whole thing. Right? This is the procedure, the length of this whole thing. Now what vectors are involved here? E1 only involves the first vector. E2 involves the first and second vector. So this guys involve the first and second vectors altogether, and that's the third vector. So E3 is a linear combination of the first 3 basis vectors here, 1, 2, and 3. Right? Similarly, if you go to E4, it will be the linear combination of the first 4 vectors. So like that, so in general, Ek will involve the first k vectors of this. Right? So that's why it's a recursive kind of procedure. You just take step by step from here, these vectors. Right? Finally, of course, the En will be a linear combination of all the n vectors. That's the idea. So this is the procedure. Of course, I mean, this procedure is fine. I mean, you can use it for finite dimensional cases, right? Because in finite dimensional, because as you see, this is a recursive step, right? So if it's a finite dimensional space, after some amount of work, maybe an hour or 2 hours of work, you can get the full orthogonal basis, right? But if it's infinite dimensional spaces, it's not very useful, right? You have to find other ways of doing it. But what this shows is that in principle, it is possible to construct orthonormal basis, right? You wouldn't use this ever to construct in the function space, which is infinite dimensional space, you will not use this method to construct the orthonormal basis. You will find some other ways of doing it. But what this shows is that it's possible. There exists orthonormal basis. For finite dimensional cases, you do use this procedure because it will just take a finite amount of time to construct the orthonormal basis. Yeah, okay. Let me see. Okay, we will come back to, let me see what I could do. Yeah, let me, yeah, okay, since I'm talking about it, maybe I can say at this point something before I move to the linear operators. You see, before I said that if I give you an arbitrary, some basis, right, if you may pick up another basis, and the relation between these two bases is given by basically an n by n matrix, which is usually called the transformation matrix. But the important point of that matrix was that matrix was had determinant not equal to 0, which means it was invertible matrix. Okay, that was the important point here. Now you can ask the following question: suppose I have constructed an orthonormal basis. You construct another orthonormal basis, right? What is the relation between these two bases? These two orthonormal bases now, not arbitrary basis, but orthonormal basis. Okay. So we can ask that question. Yeah.
Is there any difference between orthogonal and orthonormal?
Yeah, okay, sorry. I mean, usually when you say orthogonal, you don't worry about normalizing the length to 1, right? When you say orthogonal, you just mean that the scalar product of any two different ones is 0. But you don't necessarily mean that the length of each of them is 1, right? But when I say orthogonal, I really mean orthonormal, okay? Orthonormal. So I've also normalized the length to 1. Because that step is a trivial step. I mean, I think most difficult step is to make it perpendicular, everything orthogonal to each other. Once you have made orthogonal, then it's a matter of just scaling by the length, no? Dividing by the length to make it. Yeah. So really, what I mean, actually, what I'll be using always orthonormal. This is the same as orthonormal in that sense, because going from orthogonal to orthonormal is a very trivial step. Just to normalize the lengths to 1. That's the only thing. Yeah, so let's see. So suppose I'm given a orthonormal basis, EI, I going from 1 to n, and there's another orthonormal basis, EI prime. I mean, somebody else has chosen another orthonormal basis, and we want to ask what is the relation between them. Okay. Well, since these are basis vectors, as before, I can always expand each of these guys in terms of these basis vectors, right? Actually, maybe I should have also mentioned this. Yeah. Actually, even before doing this, let's see what is nice about this orthonormal basis is that you can very easily expand any vector in terms of this orthonormal basis. Okay, so take any vector A. Okay, I want to expand it in terms of this orthonormal basis. Okay. The claim is that this is nothing else but this quantity EI A EI summed over I. Which is exactly what you would do. See, this is the projection of the vector A along the EI direction. And then you multiply by the vector EI and sum it up. How do you prove that? Well, let's prove this. Let's look at EJ. Let's apply EJ with A. I want to check whether this is true or not. I want to check this is true or not. So let's multiply by EJ on both sides. Let's take the scalar product on both sides. Okay. Well, this side you have that, whereas this side you get EIA. This is just a number. Then EJ with EI summed over I equal to 1 to n. But that's Kronecker delta. Okay. And then so this is Kronecker delta. delta ji. Okay, and then this in the sum, the only terms will contribute is I equal to j, and that term you get ej a, but that's the same on both sides. Okay, so it's so therefore this is indeed true. So it's a very simple expansion. I mean, for any basis, of course, I know. I mean, this a I can expand in this basis, and coefficient, there will be some coefficients, right? Usually I just call them ai, right? But what I'm saying in orthonormal basis, these coefficients are just simply given by the scalar product of a with the orthonormal vectors. Right? So that's the idea. I mean, it's a very simple expression, a very explicit expression in terms of scalar product. Okay, so let's do this here. Ei prime, I can always expand in terms of ei, in terms of this old basis vectors. So it will be some coefficient, let me call it r, ij, ej, summed over j equal to 1 to n. Right? This is what, I mean, this is the kind of matrix I was using for an arbitrary basis. Right? Of course, also in particular, I mean, after all, this is also a basis, it's just orthonormal basis. So I can always write ei prime as a linear combination of ej for each I. Right? So, and those are the coefficients. Okay. So now let us see. But you see, this is not an arbitrary basis. We are saying that this is an orthonormal basis, right? So they must satisfy ei prime with ej prime is Kronecker delta, right? So let us see what that implies on this matrix. So let's compute, first of all, what is the dual, ei prime, the dual. Dual is simply the duals of this, but I have to take the complex conjugate of these numbers. Remember, the dual is, when you go from the, when you take the dual, it's anti-linear map, right? I mean, remember this statement. If the dual of A is, I denote by that, and the dual of B, I denote by this, then the dual of alpha A plus beta B is alpha star, complex conjugate, A plus beta bar B, right? This is anti-linear map. So the dual ei prime would be simply this guy, j equal to 1 to n, r bar ji ej, where ej are the dual of the ej here, right? This is an anti-linear map. Okay. So now let's just take ei prime with ek prime, let's say. Ei prime with ek prime, scalar product. Well, so first of all, I can, I mean, so what do we get here? So here you have maybe too many, maybe, let's see, I can, no, so let's do the following. I mean, not to, this, I keep this I, this guy I put here K, okay, K, and here, so this is K, and here I put here L, okay. I mean, not to use the same index, that otherwise if you, I mean, when you use these indices, you have to be careful. I mean, okay, I will come to that one second. So this ek prime is that, so we have L equal to 1 to n, r bar, lk, then you have el, okay. Similarly for ei prime, I have that expression, which is j equal to 1 to n, rji, and then we have el with ej, correct? That's the, I mean, I've done several steps in one step, but I think by now you should be familiar with that, right? Yeah, I'm just using linearity in both arguments, in this and that. Okay, but this guy is Kronecker delta, because the old basis, this basis, I mean, actually both the bases are orthonormal, right? So this is Kronecker delta. So what we find here is, this is L equal to 1 to n, j equal to 1 to n, 1 to n, and then we have r bar, lk, r, j, I, and delta j, delta lj. right? So I can, for example, sum over L equal to 1 to n, then the only contribution will come when L is equal to j. And in that case, the result is simply this L replaced by j, right? So one sum I can do because of the conical delta. So this is the same as j equal to 1 to n, r bar jk r ji. And this whole thing is supposed to be equal to delta ki, right? Because the new basis is also orthonormal, right? So you see this matrix R, which defines a transformation between these two bases, is a very special matrix. It satisfies this condition. So I think one way to write this, you remember what we said? We are thinking of this as J labeling the row and I labeling the column, right? As I said, that's a matter of convention, but let's fix this convention. I will take this J to be the row and I to be the column. Then this thing is simply, I can write this as, let me write it here. So let's say R, let me define the matrix R as this. So remember, J is the column, right? J is the row. So you have R1, 1, R1, 2, R1, n, right? So the top, the J index is the row. Then you have R21, R22, R2n. Similarly, Rn1 up to Rnn, right? So I'm writing of this, all these coefficients I'm putting together in an n by n matrix. Okay. Then what is R dagger? R dagger. You remember the definition of dagger? Transpose. Yeah. So this is the same as first you take the complex conjugate and then take the transpose. I just write it as T. T means transpose. Transpose means exchanging the row and column. So that matrix will be, let's write down explicitly. When I take the complex conjugate, I just take the complex conjugate of each of these guys, and then I exchange. So the row and column. So this becomes R bar 1, 1. This becomes R bar 2, 1. And so on. R bar n 1. Here, this will come there. So you get here R bar 1, 2, R bar 2, 2, and so on, and R bar n 2, and finally the last one will be R bar 1n, R bar 2n, all the way up to R bar nn. Okay? This is what is R dagger. And now let's take the product of these two matrices. Okay? R dagger with R as a matrix multiplication. Okay? So R dagger with R will be, so let's see what it is. So the first element will be this with that. Right? So you get, okay, let me just write the 1, 1 component, or let's say ij component of that, or kl component of that, kl. Kth row and nth column. So I take the kth row and multiply to the nth column. Okay. So kth row will be R bar 1 k, okay, kth row, and then lth column will be, what is the L will be down here, right? R bar RL 1 plus R bar 2k R2L and so on, right? R bar n k RNL, right? I'm taking the kth row here, kth row, and multiplying term by term the lth column. So the first one, so let me just write explicitly here. So there will be kth row will be this. Kth row will be R bar 1k, R bar 2k, R bar nk, right? Kth row. Whereas lth column here, let me write lth column, will be R1L, R2L, all the way to RNL. So this is the lth column. And that's the kth row. So I take the kth row and multiply to the nth column. So the first term is R bar 1k, R1L. Second term is R bar 2k R2L, and so on. So this is the sum, which is the same. I can write it in the summation formula. So this is R bar JK R bar RL JL summed over J, right? J equal to 1, J equal to 2, all the way up to J equal to N. But that's exactly that, right? So what we are saying is this term, this object is nothing else but the element of the R dagger A which appears in the kth row and lth column. Okay, but left hand side, this is no, this is I. Sorry, this is I, not L. This is I. So I should here put I, ith column. Okay, so this is all I read there L instead of I. So okay. So what we are saying is this is the this what appears there is simply you take the R dagger A R, the matrix product of R dagger with R, and pick up the kth row and ith column, right? That is what appears on the right hand side. Whereas left hand side, it's the saying is Kronecker delta, but Kronecker delta means it's a unit matrix, right? If you take the unit matrix and look at the kth row and ith column, that is delta ki, Kronecker delta. So we have the equation. That equation is simply R dagger R is equal to identity matrix, n by n identity matrix. That is that equation we're saying. Okay. So what this is telling you is that if I make a transformation from one orthonormal basis to another orthonormal basis given by this matrix R, then that matrix is not an arbitrary matrix. It satisfies this condition, R dagger R is equal to 1. 1 meaning identity matrix. Yeah? Such matrices which satisfy this condition are called unitary matrices. There's a name for these matrices. They're called unitary matrices. Okay. So write it this way. There's some just the definition. So matrices. So n by n matrices. Let's say n by n matrices that satisfy the condition R dagger R is equal to identity matrix. I mean, I'm using this block 1 to indicate that this is matrix 1. Okay. Then such matrices are called unitary matrices. It's very important. These unitary matrices are very important. Okay. Note that, I mean, there are some very nice features of that. Okay, first of all, what this means, that the inverse of R is R dagger, right? So R dagger is the inverse of R. Second important point is that if I give you two unitary matrices, let's say R1 and R2, you can ask the following question: is the product of these two matrices unitary or not? Okay. So take say R1, and suppose R1 and R2 are unitary. Question is R1 times R2, is it unitary or not? That's the question. So let's check it. So what I want to take, I take R1, R2 and multiply from the left the dagger of that. So I want to consider R1, R2, dagger, R1, R2. Matrix multiplication. These are all matrix multiplications. But you know that when I take the dagger, the order changes. Are you familiar with that? Right? So if I open this up, this becomes R2 dagger, R1 dagger times R1, R2. Okay. But now R1 dagger with R1 is 1, because R1 we said is unitary, right? So this is the same as R2 dagger times R2, because here this is identity matrix, right? So it's R2 dagger, but this is again unitary, so this is identity matrix. Okay, so product of two unitary matrices is again unitary, but that you should have expected. Why? Because you see, one unitary matrix took you from one orthonormal basis to another orthonormal basis. Then the second one, when you apply, that takes you to so in other words, so let's say from EI, by applying R1, I go to some EI prime basis. These are orthonormal. Right? Then I apply R2 to go to some EI double prime and even yet another orthonormal basis. So when I apply these two together, that is like going from here to there directly. But after all, this is again a transformation from orthonormal to orthonormal. So that must be also unitary, right? So it's not surprising that this product is unitary. Both R1, R2 or R2, R1, doesn't matter which order. It's still, you go to from orthonormal basis to orthonormal basis, right? So, yeah, and there are of course, that's this one property. Another property is that the inverse of a unitary matrix is again unitary, which is obvious, right? So R inverse, if R is unitary, then R inverse is also unitary. Okay, easy to see. Well, R inverse, I want to take R inverse dagger with R inverse. I want to check whether this is unit matrix or not. But when you take the R inverse dagger, that is simply R dagger inverse. I can exchange times R inverse. But this is the same as R dagger inverse. Okay, but R dagger is inverse of R. So R dagger is 1, right? So this is the inverse of the identity, which is identity. Okay, so this also. So this is a very special thing that you have. So what we are saying is that if you take the set of all n cross n matrices, the set of all n cross n unitary matrices, okay, then the product of any two such matrices inside the set will again give you another element of the same set, right? Furthermore, in this set there is also the inverse. I mean, if an element exists, its inverse exists. Of course, identity matrix also is a special unitary matrix. I mean, the identity matrix obviously satisfies this condition. If you take identity times identity dagger, that's identity, of course, right? So such a set which has these properties is called a group. That's a definition of a group. Okay. So what we are seeing is that this is called a unitary group, by the way, because it's a group consisting of unitary matrices. You call this, and usually you denote this group by UN. U stands for unitary, N stands for this n by n. Right? So such a group is called unitary group of n by n matrices. So what we are learning here is that if you take an n-dimensional vector space and consider this, start from one orthonormal basis, and then you look at all possible transformations to another orthonormal basis, those are given by unitary matrices. And the set of all these unitary matrices forms a group, right, which is called unitary group. That's one thing. The second thing, this is very important because under the unitary transformation, let's say, I mean, why is it important? Because in quantum mechanics, you will see that, for example, all the time evolution operator, time evolution. So given a state, suppose I start with initial state, quantum mechanical state, you evolve in time, right? Wait for some time and see how the state develops, right? Okay, it will be some other state in general, right? If there is some non-trivial dynamics, it will be some other state. But the important point is that other state will have the same norm with all the scalar product with everything else, okay? Which means that the transformation which takes you from initial state to final state is a unitary transformation, okay? It will be unitary matrix. I mean, of course, it will be infinite dimensional. In quantum mechanics, the space is infinite dimensional, but nevertheless, it will be unitary operator. Time evolution operator is a unitary operator, okay? So unitary operators plays a very, very important role in quantum mechanics. Okay. This is unitary matrix because I'm talking about finite dimensional cases. All right. So now, so this is the, I think, yeah. I mean, we will come back to this more also, perhaps later. But let me, is there any question here? Is there any question? By the way, if it was a real, I mean, this was, I'm always talking about complex vector spaces, right? But if it was a real vector spaces, then these matrices R will be real, right? In that case, the complex conjugation does nothing, right? So this equation will simply become R transpose R, because dagger is the complex conjugation and transpose, but complex conjugation does nothing because the real matrix, right? So this equation becomes R transpose R equal to 1. Okay? And R transpose R equal to 1, the real matrices will satisfy that condition. Those matrices are called orthogonal matrices. Orthogonal matrices. Okay? And you are familiar with it. I think you from the geometry, the planar geometry, you already know these matrices. For example, so let's see in the real case, in the case of real vectors, real vector spaces, R is real, the matrix R is real, and then this equation R dagger R is the same as R transpose R, right? Because complex conjugation is the same, doesn't do anything because the matrix is real. So this is equal to identity. So such matrices are called orthogonal matrices. Orthogonal matrices. Okay. So this is orthogonal matrix, n cross n orthogonal matrices. And this again, you can show this forms a group. Product of two orthogonal matrices will again be orthogonal. You can go through the entire proof. And this group is called ON, orthogonal group. ON. Group. Yeah? So to show to you that you have already seen these groups, let's consider n equal to 2 case, two-dimensional space, two-dimensional real vector space. So in two-dimensional, so take n equal to 2 case. So I have this is my plane, and I choose an orthonormal basis. So let's say the usual x-axis and y-axis with the length 1. So this is one vector. That's another vector, length 1. Okay. This is E1 and E2. Now, suppose I want to choose another basis, which is orthonormal. How would you do this? Well, suppose I can rotate. I rotate this whole thing. There's one way to get in, right? I can rotate by an angle theta, so that this E1 goes to this E1 prime, and this E2. Let me write E2 is here. E2 will become like that, right? E2 prime. And this angle is theta. Okay. And you can see what is this. I mean, you can write down what is this is E1 prime. Sorry. So E1 prime is simply, you can see what it is. If you project it, this becomes cosine theta times E1. So cosine theta times E1 plus sine theta times E2. Right? If you project it this way, this projection will be sine of theta, right? And E2 prime, because I mean there's no other number because E1 prime length is 1. Remember, E2 prime will be, see, E2 prime is this one. So when I project along the first axis, it's in the negative direction. So you get here minus sine theta E1 plus cosine theta E2. Okay. Which in the matrix language you can write like this. So E1 prime, the way we introduce the matrix E1 prime, E2 prime. This is the same as cosine theta, sine theta, minus sine theta, cosine theta, E1, E2. So this is a matrix R in this case. And indeed you can check that this is orthogonal. Okay. So this is R. So R transpose is simply cos theta. I have to exchange these two, right? So minus sine theta, cosine theta. And now I multiply with this, this with that. So first row with the first column, you get cos square theta plus sine square theta, which is 1. Now take this guy with the second column. This becomes cos theta sine theta, and this minus sine theta cos theta cancels, right? So off diagonal term is 0. And similarly, you can check with this, right? So indeed, you can show that R transpose R is 1. Is a 2 by 2 unit matrix. This is, but you see, it's not just a rotation. Rotation is one way to get another orthonormal basis. But you could also do a parity transformation. You know what is a parity transformation? Just reflect. So for example, reflect along this. So reflect everything about this axis. So E1 goes to minus E1, right? But E2 remains the same. That's again gives you an orthonormal basis, right? So this is the full O2 group. This O2 orthogonal group, 2 by 2 matrix, consists of two types of transformations. One is a rotation, okay, and other is a parity, reflection and rotations. In general, this ON is again the same thing, but now you have to consider all possible rotations in n-dimensional space, right? So for example, if you take n equal to 3, O3, so our real three space-time dimensions, space dimensions, it will be all rotations in three-dimensional space, together with all possible reflections. That is what this group is. Okay? That is the meaning of this group. The rotation group together with the parity, the reflection. So, okay. Can I, let's see how much more, maybe, at least let me introduce the concept of linear, if you don't have any questions here. Let me introduce this concept of linear operators, because that is now the main thing. So far it was all just, yeah, okay. Okay. Actually, so now I will discuss something called linear operators. Okay, we have vector space. We have even a scalar product inside this vector space. And now we want to study various operations on this vector space. Actually, these were particular examples of that. These R matrices and so on. Those are certain examples of transformations. You apply this on some vector, it will give you again another vector. Right? But so let's define it more generally. So we have linear operators. I will just define it, and I will just stop after that. So the notion of linear operators. Well, we have already seen an example of this. So more general. So let me define it. So let's say S is a vector space, and let's say, I don't know, something else, give a name to that. Some V is another vector space. So these are two vector spaces. S and V are vector spaces. So in general, you can define an operation. So you define a linear operator, let's call it A. A is a linear operator. What it does, it maps S to V. Okay. So it takes, for every element of S, it gives a rule to associate an element of V. But it should be also linear. This is the important point, linear. Right? So what it means is that A acting on, say, two vectors, say sum of two vectors, alpha A plus beta B, here, will be the same as alpha A acting on A plus beta A acting on B. This is a linear operator. This is an element of that. This is an element of that. Right? And I'm saying A maps vectors of S to vectors of V. Right? So this is an element of that. This is an element of that. Linear combination of these two is again an element of that. And the particular thing we have already studied when we defined the dual vector spaces was linear functions. So what is special about linear functions? In the linear function, this V is just a set of real numbers, set of complex numbers. Okay, we will talk set of complex numbers, which is an example of a vector space. After all, the set of complex numbers is a vector space, or set of real numbers for that matter is a vector space. Okay, you can check. It's a one-dimensional set of real numbers is a one real dimensional vector space. Set of complex numbers is a one complex dimensional vector space. Again, you can check that they satisfy all the conditions. Yeah, please check that. Check that the set of complex numbers is a vector space, is a complex vector space of dimension 1. Right? This is a complex dimension 1. So I mean you can check that. So what I defined before to define the dual vector space, it was just a special case of this, where this V was this particular vector space. Okay, but now we are generalizing this concept. This from S to V. V is an arbitrary vector space. So this is an important point. This is a map from S to V, which is linear map. Okay, this is the important point here. Now, in fact, what we will be doing is actually in most of the physical applications, really, what appears is when V is actually equal to S itself. Okay. Yeah, so this is defined for any V, for any S and any V. Defined. But what appears in physical applications mostly is the case when V and S are the same. Okay. So, for example, in quantum mechanics, this S will be the Hilbert space of states, of physical states, right? And A will be all the possible operators, Hamiltonian or whatever operators you have. When they act on the vector state, it will give you again a state in the same Hilbert space, right? So in particular in quantum mechanics, the application which appears is when S is equal to V. S is equal to V. So the special case is when V and S are the same, V is equal to S. So that the map is from S to itself. Okay. So this is the basic definition. And once again, you see, for a finite dimensional case, you can, once you choose a basis, so for a finite dimensional case, let's say n dimensional case, once you choose a basis, 1, 2, etc., not necessarily orthonormal, just choose any basis, linearly independent, of course, that's the definition of any basis. Then I can always, so I can ask the question, what happens if I look at A acting on ith basis vector? Then of course this will be again some vector of S, right? Because I'm considering now this case where A maps S to S, right? So this is again a vector of S, therefore I should be able to expand it in the same basis, right? So it will be again some J and A, J, I, summed over J. Yeah? And these are the coefficients, whatever the numbers are, some complex numbers in general. So you see, you can represent A in terms of again an n by n matrix, where I goes from 1 to n and J goes from 1 to n. So once again, it depends on the convention, but maybe the convention used is J is the row and I is the column. Okay. So and this numbers completely define to you how A acts on an arbitrary vector, right? Because an arbitrary vector A is simply AI I with some coefficients I, right? And then you can see that A acting on A is use linearity, is a linearity property. So that is sum I equal to 1 to n AI A acting on I, which is summed I equal to 1 to n AI AJ AJI J, right? I just use this formula. So there's a double sum here now. J equal to 1 to n and I equal to 1 to n. Okay. So if I mean this object will be some new vector. I mean after I apply this again, I can rewrite it as some A prime. Let's say A prime J, right? I mean this is after all again a vector. So I can again expand on this basis, right? Now comparing these two, you see what happens. This A prime J is nothing else but AJI AI. Yeah. Okay. In the matrix notation, so let me write it. Sorry, I'm being fast here because we have seen this many times in different situations. We have seen this kind of many times. So you should be familiar by now. So let me arrange these things as a column vector A1, A2, A3, AN. Call this as A, column vector A. Similarly, A prime is A1 prime, A2 prime, AN prime, and A, write it as this matrix. So A11, A12, A1n. You see, J is the upper index is I'm taking the upper index as the row, and the lower index is the column. Then that equation, I can write it as a matrix equation. A prime equal to A matrix equation. So these are column vectors, n column vectors, and this is an n by n matrix. So this is an n by n matrix. This is n rows and 1 column, so n cross 1 matrix, and this is also n cross 1 matrix. So the matrix multiplication, you see this product is again gives you that. Okay. So this is the. So the upshot is that in finite dimensional cases, if you choose a basis, the vector space itself can be represented as a n column vector, right? You see, any vector A I can expand like this and just arrange these coefficients in a column, right? Then that represents any arbitrary vector. I mean, by changing these numbers, you get different vectors, right? So the vector space is isomorphic or represented by just a column vector, n dimensional column vector, right? If you start with an n dimensional vector. Once this, of course, choosing a basis, and the linear operators again in that basis are represented by n matrices. Right? So matrices are completely general. I mean, in some sense, for any finite dimensional vector space, any linear operator can be expressed as an n by n matrix once you choose a basis. So therefore, in the next week I won't be here, but the week after we will continue with this. So we'll start studying the matrices in much more detail now.